Hello and welcome to part 16 of our Python programming series. Today we will explore the ordinary least squares optimization algorithm. In part 15 we covered the use cases for linear regression in machine learning. We covered the training process and finally we also covered the three key scikit-learn statements used for training linear regression models. So in this session, we discuss about roll-up optimization algorithms in ML. So if you look at the definition, it says that it facilitates the process of finding best possible model parameters that minimizes the objective or loss function. If you're talking about linear regression, then the model parameters are nothing but intercept and coefficients. So optimization algorithm will estimate them, will give the best possible parameters by minimizing what is called as objective or loss function. So we'll talk about what is optimization algorithm and if it is linear regression model, what kind of optimization algorithm we use and about the objective or the loss function. In machine learning, we come across different types of optimization algorithm like gradient descent, momentum-based method, adaptive learning, ordinary least squares, etc. I have highlighted ordinary least squares because this is what we are going to discuss in this particular session. The reason is this is used in linear regression model when sklearn fit function is used for training. So when you train linear regression model using sklearn fit function, actually we use OLS optimization algorithm. In this slide, there are two mathematical equations shown. This one is the learning function for linear regression and we are familiar with. And this is the objective or loss function which is used in the case of OLS, ordinary least squares optimization algorithm. And this needs to be minimized. When this is minimum, we get alpha and beta. If you look at the learning function, alpha and beta are the parameters. Alpha is the intercept, beta is the coefficient of x. We will look at the objective function or loss function in the case of OLS, which is given here. Now, if you look at this mathematical function, you have yi, which is nothing but observed data point or the target or the output variable of ith training sample in the given data set. For example, if you look at this, there are 5 training samples. So this is the first one, second, third, fourth, fifth, and x and y, which forms our labeled data set. So I'm just taking a very small data set to understand how this function works. So x and y both are given here. So if I say I equal to 1, then I'm talking about this particular x value. So this is going to be xi and this is going to be my yi value. So there are 5 values training samples here. So I will range from 1 to 5 in this case. But in general, I value can range from 1 to n where you have n training samples. So this is the objective function and we actually compute the sum of squared differences between the observed data point, so that is this one, and the predictions made by the model, which we saw in the learning function earlier. And the prediction for the model to predict, it requires alpha and beta along with corresponding x values. So once alpha and beta are given, then model can perform predictions and you get a yi cap. And we want to bring the gap between yi cap, which is model predictions, and the observed data point, which is as per the given data set, to a minimum value. When it is minimum, you get the best alpha and beta values or optimal alpha and beta value. So that is the main aim of any training process, to estimate alpha and beta, and for that the objective or the loss function is required. And with OLS, this is the objective or the loss function used. Now using calculus, I will not go into the derivations here. We can directly compute alpha and beta using these formulas. So this is beta. Beta is nothing but the coefficient. There is only one coefficient because only one x value we have, and this is the intercept. In the case of linear regression, intercept refers to the starting point of the line. Purpose of linear regression training or fitting is fit a straight line with a given slope which is beta and the starting point which is alpha, which is nothing but intercept or bias. So we can compute beta and alpha directly using these mathematical functions. And if you look at this, let us say we'll focus on beta first, and once you have the beta value, you can compute alpha using this particular function. If you look at this, there are n training samples, as we saw in the previous case, 5 training samples, I equal to 1 to 5, but in general n training samples will be there. So if you look at this, this is the function. We need x mean, we need a mean value of x or the average value of x, and mean value of y or average value of y. With that we can compute beta. So that means we are given a labeled data set, we are given x and y, and with the help of x and y we can compute mean x and mean y, and then we can substitute them and we get beta. So this is how manually you can manually also you can do that. You can compute it, or you can use a NumPy functions, so then you can compute beta. So as you can see here, this is the mathematical function for beta, this is for alpha. First we compute beta, which we have the data set here. We have x with 5 training samples, so I equal to 1 to 5. Then we have, from this we can compute x mean. There are 5 values, we add them and divide by 5, we get 2, which is mean value of x. Now similarly, to get mean value of y, we add them and divide by 5. There are 5 training samples, 5 values here, so we get 4.4. So x mean and y mean we computed and we can substitute them, so we get 2.2 for beta. Once we get beta, then we can compute alpha using this function, which requires mean y, mean x and the beta, and in this case it's going to be 0. So beta is 2.2, which indicates the slope of the straight line which we are going to fit after the training process, and alpha is 0, means our line starts at origin, x equal to 0, y equal to 0. Our starting point is 0 in this case, and this is the slope of that. So this is what we understand. So this is the method 1 which we follow, and we got 2.2 for beta and we got 0 for alpha. But we want to verify this using NumPy functions, and for that there will be a demonstration session. I will use Jupyter Lab for this. And now once you do that, once we verify using NumPy functions, and we found that manual method and the NumPy based method both give the same answer. After that we want to estimate alpha and beta using fit function of sklearn, because so that's why this session is important, because fit function uses OLS. So we already verified OLS, and that gives alpha and beta as 0 and 2.2. Now we want to use the direct fit function, and that also must give alpha and beta, which is same as method 1 and method 2. So this is what we are going to discuss in this session. So move on to the demonstration session. I will take you to Jupyter Lab. So now let us see the demonstration, and method 1 is manual computation, which we just saw. These are the two mathematical functions for beta and alpha, and we already computed manually using this function, and this is the sample data set that we have. So we got mean values for x and y respectively as 2 and 4.4, and when we substituted here these mean values along with x and y, we got beta as 2.2 and alpha as 0. Now we want to verify this using NumPy functions. So I'm using Jupyter Lab, and this is the notebook. So I imported NumPy library here, as you can see, and I generate x and y using NumPy array function. And you can see that x and y are exactly same as that I have used in my method 1. So this is x, this is y, you can see that. So same values are used so that we expect the same beta and alpha values in this case. So once you generate them, now we compute mean values of x and y. For that I have used a mean function of NumPy, and I call this as x mean and y mean. So let me just run this cell, and let me print x mean and y mean. So we got earlier x mean as 2 and y mean as 4.4. So let me check what we get. You can see that x mean is 2 and 4.4. So we got the same values when we used NumPy functions. Alright, so once you compute mean values, then we can compute beta and alpha using again NumPy functions. So these are the two mathematical functions. So let me solve for beta and alpha using NumPy functions. So this is the numerator of beta, this is the denominator. I can use some function for this one, and mean already I have mean values of x and y already I have computed. So this is numerator computation, and this is for the denominator, and this is how I can get beta. And then once we get beta, that you can substitute here as shown in this mathematical function, and we get alpha here. So let me run this particular cell. You can see that we get coefficient as 2.2 and intercept as 0, which is same as the manual method. Here also we got beta 2.2 and intercept as, that means alpha as 0. Now what is important is we want to verify this using sklearn fit function. So because fit function is used for training linear regression model, and fit function uses OLS method. So OLS method has been tested manually and using NumPy functions, and we got coefficient as 2.2 and intercept as 0, and we want to verify this using fit function of linear regression. So for that we need this particular linear regression class. We import from linear model module of sklearn. Then we created the class, which we these codes we have already seen earlier, so you are familiar with this. So we create the class, and we need to reshape x. That means we need to convert x into column vector. Earlier both were row vectors for fit function. So after that you can input this x and y, and then we can fit the model on the data set on these x and y data. So once the fit process is done, that means once we train this, after that we can compute the intercept and coefficient of this model. So then we can print this. So let me just run this particular cell, and you can see that the coefficient is 2.2 and intercept is very close to 0. So let me just round this beta values to 1 decimal point and check. So you see that coefficient beta is 2.2 and intercept we got it as 0. So this clearly shows that the fit function of sklearn for linear regression uses OLS function. So we have all the three methods give the same alpha and beta, and that's how we verified it. In the next session we start discussing about other machine learning models. We discuss about binary classification model, and there again we use another version of regression which is called as a logistic regression model.